Thank you all for coming. Uh, those of you who were here before, I did a talk on Cherry Alliance. So now I'm going to go from my Cherry Alliance hat to my low-risk hat. I'm a principal hardware engineer at Low Risk, and I want to talk to you about how you could build your own SoC with IP that's already out there. So first I want to talk about OpenTitan. So OpenTitan has been our flagship project for the last 10 years or so. And as part of this project, we've kind of built up a huge IP library. So this is kind of a block diagram. You can see on top there, you see our IBEX CPU. And we've built up all these hardware IP blocks essentially from scratch because we wanted to have correct provenance so that people could use these in an open source and permissive way. So this is all open source. You can find it yourself. You can reuse it. It's taped out. It's going to be going into the next generation Chromebooks. So this is really exciting. This is taking open source silicon really to the next level. So I want to show you in this tutorial how you can kind of take any of these IP blocks that you might want and create your own chip. So the inspiration for this talk came from my work on Sonata. So if you were here for the talk previously, they were talking about Cherry. So we have this board here. It's an open source PCB. You can go download it yourself, manufacture it yourself. You can also buy the board on Mouser. But what you can see here in the gray block is the FPGA. So the FPGA essentially houses an SoC. So that's a chip, a system on chip. And it has this IBEX core and a TIE-Link bus and lots of IP blocks. So I wanted to show you like how to bootstrap such a system and do it yourself. So what are we going to do? We're going to do something very simple. Okay, so I'm hopefully going to do this in like about 15 minutes. Show you how to make a simple simple chip designed with an IBEX CPU and 2 peripherals. So we have a RAM to be able to put our program in, and our UART to be able to do serial output, input and output. And then we have a bus to connect them all up. So how do we get going with this? Looks very simple. First of all, we have Git. So I'm assuming here that you're going to create your own directory, and you're going to initialize your Git repository in there. We're going to create a README file, relatively simple. We're going to put this in this README file. And then because we don't want to do everything, kind of reproducing everything, I've created this repository that you can pull things off of called SoC Easy Build. And I've kind of created a .gitignore for you. You don't have to write any of these things down, by the way. There's a website at the end, and it'll have all the instructions for you. So I'm downloading this .gitignore file, adding the README and the gitignore, and then making my first commit. So this is relatively simple. Most people will know, but you don't have to use Git, obviously. You can use any repository management you might want. Okay, then maybe something a little bit more that you might not be as familiar with. So vendoring is a way to pull in dependencies. So this is how we're going to pull in our UART, pull in our IBEX into our repository. You don't have to use vendoring, but this is the flow that we use in OpenTitan to pull in IP, so that's why I'm using it here. But you could just as well use submodules or just copy-paste source code. But we like vendoring because you have a little bit more provenance, et cetera, and it's a nice controlled mechanism that at least I understand. So how do we do this? So there's this Python script called vendor.py. We're pulling that in from the OpenTitan repository. So that's nice. We're going to make this Python script executable. And just running this vendor.py will be a bit difficult, so I've also made a Python environment or a specification of the Python environment called Python requirements.txt. And now we're going to set up this virtual environment and install the Python requirements that we need to run our system. So we're creating that virtual environment. We're activating this virtual environment now. And then we are using pip to install the Python requirements that we downloaded earlier. So this does a couple of things. It builds Fuse SoC, which is our build tool for our SoC, and it also installs all the dependencies that we need to write to run our vendor utility. So now we're going to test that. We're going to do util. We're going to first add things to the to our Git repository. Sometimes it's very slow when you're typing. And then, so we see that we have our Python requirements and our vendor thing, and then we're just going to test that we can run our vendor.py. So this is all fine. This is, again, not super exciting. It's all kind of boilerplate stuff. But now we're getting to a little bit more exciting things. So IBEX is low-risk CPU. It's an embedded 32-bit processor. Now we want to pull this into our repository. So first of all, we're going to get a HJSON file which essentially specifies where to find IBEX. So if we look in this low-risk IBEX vendor.hjson, we can actually see that this tells the vendor utility where to find it. So this is a GitHub repository, nothing super exciting. So we can add that to our Git repository because the vendor utility also handily creates Git commits, but we first have to make sure that we have a clean working directory, so we do have to make this commit first. And then we're actually going to invoke our vendor utility. First go into our Python environment, otherwise the utility won't run. And then we're going to say, okay, pull this low-risk IBEX repository and put it into our repository. So now we can look in this vendor directory, low-risk and low-risk test IBEX, and we see that we have essentially a copy of IBEX in our repo. So that's really nice. We don't have to rewrite IBEX, it's just there. Okay, so that's just the left part, right? So we need 3 more things. We need the UART, we need the RAM, and we need a bus. That's what we need to create the rest of our chip. So we're going to get the rest of the stuff from OpenTitan, which I mentioned earlier. OpenTitan has a way to generate buses, and it has this primitives for the RAM, and also the UART IP. So how do we do this? Again, we find this vendor.hjson. In this case, it's for the low-risk IP or OpenTitan IP. Again, we can look into this vendor.hjson, and it's essentially a pointer to our OpenTitan repository. So you can see here that it points to the github.com low-risk/OpenTitan. So that's really nice. This is where the tutorial gets a little bit ugly. I tried to make it as clean as possible, but I also wanted to make it complete. We do need a few patch files to remove a couple of like OpenTitan specific things. But luckily, we can kind of pull these patch files from other repositories. So I'm just going to do a couple of wget commands. For those of you that can read quickly, it does things like removing some of the integrity checks and the alerts. And some of the times, it also removes certain dependencies from the core files, which aren't really necessary, just to make our build a little bit cleaner and that we don't have to pull in all of OpenTitan. Because I also wanted to make sure that this was as small as possible. So we're pulling in all these patch files. Luckily, these patch files, part of the cool thing about the vendor utility is that you can pull in your repositories, but you can also automatically apply these patch files. So now we have a list of patch files. We have in this directory, we have some patch files to different things. So the TLUL and the UART are maybe the most interesting ones there. Those are the tiling bus and the UART that we need. So we're going to commit all these patch files just because the vendor.py utility needs a clean working directory. I'm going to say lots of patch files is our commit message. And then we're going to go into our Python environment that we set up previously and then run our vendor utility again. And this time it's going to pull in all of OpenTitan, pull out all the parts that it needs, so that's the UART, the tile link, etc. Apply the patches that we just downloaded, and everything should now be in our repository. So this is great. So we've pulled in everything. The problem is that or the problem now is that we need to have a crossbar that's specific for us. So usually every chip has its own crossbar. So again, we can use the repository that I made, the SoC easy build, and there's this xbar main.hjson, which specifies what our crossbar should look like. If you now we're going to make a make a directory where things will live. Now we're going to use this tlgen.py, which we pulled in from OpenTitan, which essentially generates your tile link. Input the xbar.hjson, which is the specification of our crossbar, and tell it to output into the directory that we just made. Now we're going to do a bit of cleanup. We don't really need the kind of verification stuff that it generated. We can always regenerate that later if we do need it. And we're going to do a little bit of cleanup here as well. Again, all these commands, I'll share a link later where you can find them. So looking in here, we see that we have two system Verilog files there. And if we look into one of these, which is the TileLink main package, we see that it specifies where our RAM lives, so which address, and also where our UART lives. So that's useful. This is essentially which addresses are used. And it also tells us that we have two devices, the RAM and the UART, which is what we want, and one host, which is the IBEX. So it's a very simple bus, but it is nicely auto-generated. Okay, so now we have everything, or at least each individual part, but let's actually put it all together. So let's create a simulator, and we want to use Verilator in this case. So first of all, we're going to go back to our SoC easy build directory that I created for you, and there's an RTL/SoC module, so that's our chip module. And if we look into this RTL/SoC module, you'll see that it instantiates all the things that we need. So if we look for the UART, which is called U_UART, you can see that it has a receive and a transmit. So that's nice. If we look for our RAM, you can see that we have a RAM and we have two ports on it. We have the data side and we have the instruction, so it's a 2-port RAM. And then also we can look for our crossbar, which we auto-generated, and we can see that it's connected on the host side to the IBEX, and on the device side to our SRAM and our UART. So to be able to run our simulator, we need a few more things. First of all, we need a kind of top module on the system Verilog side, which instantiates our chip module that we just inspected. And we also need a C++ file to tell Verilator how to interact with our system Verilog. Finally, we need something like a make file, but in this case, it's a core file for FuseSoC to know how to actually build this thing, right? So this is called soc.core, and it tells it, okay, look for this low-risk IBEX thing that we need to use. We look for the UART, and look for our crossbar that we generated. And also, we tell you how to connect everything in this SoCmod thing. So it's essentially a make file for FuseSoC. And so now we can use FuseSoC, which is our make system for our SoC. We tell it where to find the core files, the core file that we just downloaded. It'll also recursively go through all the kind of things that we've entered in. We tell the tool is Verilator. We want to use Verilator. And we also tell it what to build, which is called Marno SoC main in this case. I made a typo. So let's correct that typo. Instead of core root, it's called cores root. And now it seems happy. It generates all the stuff that we need, and then it says building simulator. Cool. But that didn't really do very much. So let's actually run something on there. So let's actually get a very simple program that just outputs hello world onto our UART. So first of all, we get a boot.s file. It's very boring, but essentially just is some assembly code that starts up and sets up our stack and jumps to our main loop. Then we have our actual hello world.c, and if we have a look into this file and search for hello world, it's the main function. It puts this string hello world onto the UART. So that's fun. We need a few more things. We need to tell the linker what to do. So this essentially tells the linker where to put things. So we specified where our RAM was. So this link.ld tells the linker where to put things. And then we also have this script that I put together, which is called build.sh, which probably should be a makefile, which I will probably change in a later iteration of this tutorial. If you look into here, it's essentially just 3 bash commands, but it produces this hello world.elf that we can run on our verilator. So from the previous slide that I say, first of all, we need to make this build script executable and then run our build script, which actually produces this hello world.elf. And then we can use the build from verilator, so this is an executable, and tell it to load a certain elf into our RAM. So this is actually running our chip in simulation, and then we can look into this log file, and it says hello world. So that's nice. And that's it. So not super impressive, but it gives you a initial system to start out with, and you can start adding peripherals, whatever you want, right? So I showed you this earlier. You can take any of these blocks. If you want some AES acceleration, KMAC acceleration, etc. Take it, put it on there, regenerate the crossbar. It kind of gives you all the tools you need. And I already told you before that I used this exact method to create Sonata, essentially. So you can have, well, there's lots more IP blocks here that you can use. And as I promised, there is a website here, so techruse.com/tech, and that QR code goes to that as well. So this is a tutorial where you can find all the commands that I just showed you, including all the GIFs that I generated. Yeah, hopefully you find this useful. Yeah, that's it. Any questions, or is beer calling? Sorry, yes. Yeah, very acronym heavy, yes.
Crossbar, it just showed me fitness.
It's essentially a bus for data. So it's like, it's a crossbar because it's like your host is trying to talk to lots of different peripherals. So in this case, it's the RAM and the UART. And so it tells it how to kind of, route the requests from the hosts to all the peripherals. And that's why it's called a crossbar, because it crosses, there's a lot of crossing of wires going on there. Yeah, so this just shows you how to do the simulation environment. So FuseSoc, so when we were doing that FuseSoc command, it said --tool verilator. So you can change that to like a synthesis type of tool. For Sonata, we use Vivado because we have a Xilinx FPGA, but there's no reason why it can't use any other tool. You can even do kind of synthesis to ASIC, right? Like FuseSoc is kind of agnostic of which tool. That's currently not in this repository, but I can point you to how to do things in the Sonata repo or other repos as well. But thanks for the question. Great. Well, so Low Risk is a CIC, so we're non-for-profit, and Well, and we're a community interest company, so we want to make open source silicon a reality. So that's what we're doing here, essentially giving it away for free. I showed you a little bit about OpenTitan. So OpenTitan is a consortium of lots of companies, and they pay into the fund to fund OpenTitan work, for example. Sonata is part of the UKRI DSBD, which we heard about before. So that's government funded. So we get funding from lots of different places. We try to be. Cool, thank you all for coming. I don't want to keep you anymore. Go have fun outside, and yeah, thanks for coming.